In this video, we're going to see what a p-type semiconductor is. To start with, let me take a intrinsic silicon, which is represented by its band and bond model. And let me take this to be at a temperature of 0 Kelvin, where all the bonds are intact and all the energy states in valence band are filled with valence electrons, and the conduction band is completely empty. Let me take this intrinsic semiconductor and add some impurities, or let's say dopants, in a controlled manner, which is called as doping. And let's say these impurities are trivalent in nature. So examples of this trivalent, let's say it is boron, aluminum, gallium, indium. So let me take a boron as example for doping this intrinsic semiconductor. After adding these impurities, as we have talked about boron, before we do the modification to this band and bond model, it's a good idea to understand the electronic configuration of boron. Boron's atomic number is 5. And if you see its arrangement, it is 1s2, 2s2, and 2p1, which means in first shell we have 2 electrons, second shell we have 3 electrons, so it makes up a 5. The outermost shell for boron is the second shell, which has 3 electrons. So this is basically a trivalent impurity. So that's what we have talked about here. It's a trivalent impurity. So once we add this trivalent impurity, now let me assume one of the silicon atom in this diagram gets substituted by this boron atom. We call this substitutional doping, where it has 3 valence electrons which are participating in the bond formation with the neighbors, and it doesn't have the 4th electron to form the bond. Now the 4th one is basically an empty state, but it is not yet a whole unless we confirm it from the band model. So now let us see how it impacts the band model. Now the amount of dopants that we have added with respect to the number of silicon atoms per centimeter cube, if you compare, the doping is usually in the order of 10 power 14 to 10 power 19 or 20. But the number of silicon atoms we have per centimeter cube is 5 times 10 power 22 per centimeter cube. And if you see even the high doping that we are talking about, which is 10 power 19 over 5 times 10 power 22, we are pretty much adding just one impurity in 5,000 silicon atoms, which means for every 5,000 silicon atoms we are adding one impurity. The addition of these impurities is not going to change the basic structure of silicon, so basically it will still be silicon itself in terms of structure, but its electrical properties will be changed. Now, because the boron atoms are so insignificant in terms of number with respect to silicon atoms number, so we can assume this to be a hydrogen model and just get the energy level of boron. It seems the energy level of boron would come somewhere very close to the valence band edge, the EV, and it will be somewhere here, where we can say this energy level represents the vacant space that we are talking about here, which means there is vacancy at this energy level. Now this assumption is at T equals to 0 Kelvin. And this vacant state is actually not filled with any electrons. But we cannot call this actually a hole because this vacant state is not present in the valence band. So this is present somewhere in the energy band gap, but closer to EV. Now this energy level, we don't know what to call at this point of time, so we will name it as we go forward. And now let's say we increase the temperature to T equals to T1 Kelvin, where T1 is greater than 0. As we are increasing the temperature, the electrons in valence band can actually fill these states that are present because of the doping that we have done. And this energy difference is far less compared to the energy difference from EC to EV. So that's why these valence electrons will feel very easy to actually fill these states. So basically we'll have electrons filling here. As a result, what happens is there will be vacant states created in the valence band. So which means we have holes created in the valence band, but there are no electrons as such in the conduction band. As we are having temperature, some of the electrons from valence band might actually get enough energy to see themselves in the conduction band. So the electrons that see themselves in the conduction band will give rise to holes in the valence band. As a result, if we see here, the number of holes present in the valence band is far greater than the number of electrons in conduction band. Because the carrier concentration of holes is majority, we call this type of semiconductor as a p-type semiconductor. And now let us see the understanding from Bond model as well. The empty state that we have here is actually not the hole at this point of time. Only when, because of temperature, a neighboring electron actually moves into this one. So it fills this spot and a hole is actually created here. So this is what is called the hole. Now if we observe that the boron atom is actually taking an electron from the neighbor, so it is basically accepting. So we will call this an acceptor atom, or the doping that we have done, we'll call it acceptor doping. And the energy level that this doping has introduced, we'll call it as acceptor energy level. And the doping concentration we did, we'll call this N suffix A, representing the acceptor concentration level. And this is a number of dopants per centimeter cube. Because it actually accepted an electron, this trivalent impurity we added actually becomes a negative ion because it has one electron extra compared to its neutral state. So now we can say the states which are actually filled with the electrons, we can call them as negative ions that are present here. Just for comparison's sake, let me take the intrinsic semiconductor at T equals to T1 Kelvin. When we increase the temperature in intrinsic semiconductor, we know some of the electrons would get enough energy to go to conduction band. So we'll have electrons in conduction band, which would leave empty states, which we call holes in the valence band. And the number of electrons that are present in conduction band would be equal to the number of holes in valence band for an intrinsic semiconductor. So when we compare with intrinsic semiconductor, the hole concentration is far greater than the electron concentration. That's why we call this semiconductor, which is doped with trivalent impurity, a p-type semiconductor, which is also called as extrinsic semiconductor, because we have external material added in controlled manner into a pure intrinsic silicon or semiconductor. What if we added the other elements like aluminum or gallium or indium to form this p-type semiconductor? In that case, the only difference would be the difference between the energy level EA introduced in the energy band gap. So we can call this EA minus EV energy level. This value would be different for different doping that we do. So for example, for boron, this value is 0.045 electron volt. For aluminum, this value is 0.067 electron volt. And for gallium, this value is close to 0.072 electron volt.